Thank the organizers for giving me the opportunity to talk this in this very nice hybrid workshop. I actually has been visited the in person in Toronto. It's a very nice place, but unfortunately I cannot visit this time. So my talk will be in the opposite direction of Enrico. He wants to get away from SPS. I want to get closer to SPS. So I talk about energy dependence of the open and the hidden heavy flavor production at the RHIC. After a short introduction, I will talk about open heavy flavor and then the Quarkonium, the one slide on outlook. So heavy flavor is really a good proof of the Quark-Gluon plasma. So such as so it's similar as the muon tomography. So some people is use the cosmic ray muon to probe the hot media in volcano. So through the scattering or absorption of muon in the mountain. So in heavy flavor, actually, we can also use similarly, we can use the heavy flavor, which was produced before the QGP. So for the open heavy flavor, heavy quark, it will be interact with the medium and then hydrolyze whether pick up a lead quark from open heavy flavor hadron or pick up sorry, pick up anti-heavy quark to form this quarkonium. And for quarkonium, so due to the hot medium effect, it could be dissociated into open heavy flavor hadrons, and some of them are still survive. So if we measure the open heavy flavor or quarkonium, we can gain some information of the medium. But it's difficult because for the initial condition, the production mechanism of the heavy flavor actually is not well understood, and we also know that the crucial contribution from the cold nuclear metal effects. And for the transport of the heavy quarks in or quarkonium in QGP, so the property of the media and its evolution is not well understood, and also actually the interaction, how the heavy flavor interact with the media is not well understood. And for the hydrogenization, this competition of the coalescence and the fragmentation, and we still have some problem to understand even the Chang hadron production in proton-proton collisions compared to the dielectron E+D- collisions. And also still some contribution from the transport in hydrolytic phase. So it's really complicated, and plus for the experimentalist, the measuring the heavy flavor hadrons is also very challenging. So we really need to do really comprehensive measurement of the open heavy flavor and the quarkonium to understand to get some information of the QGP. So one thing what we can do is we can tune the QGP parameters and then mirror the same thing, similar things for the hadrons. So one way we can do is to scan the beam energy. So here we show the phase diagram. So see if we collide the scene system at different energy, actually the initial temperature is different, and also the trajectory in this phase diagram is different with different energy. So they by scanning the collision energy, probably we can add in another dimensional to hopefully to provide more information. For example, Xindong already showed this plot. You see the heavy quark diffusion coefficients as some temperature dependence. So if we measure the heavy quark in different system at a different energy, probably we can also have some information, provide some information of the temperature dependence of the diffusion coefficient. So here I show you the data set for the energy dependence study at the RHIC. So actually RHIC accumulated many data at the top energy. So the largest data set is the taken in 2010 and 2011, about 1 billion, and then also in 40 and around 40 and 16, about 1.8 billion with the heavy flavor tracker. which allows to do the secondary vortex reconstruction for open heavy flavor measurements. And in 2010, we also have some data at the 62 and the 39 GeV about 50 or 90 million mean-based events. And in 2017 and 2018, the end of the Beam Energy Scan Program 1, we also collected 54 and 27 GeV data, 1.2 billion and a half billion. So unfortunately, Phoenix decommissioned in 2017, so they don't have this kind of data set. Only Star have this data. And also for BS2, so they in 2019, they also from 2019, there's many data below 20, so from 18.6 to 7.7. However, if you look at the total chunk cross-section and the gypside cross-section as a function energy, we know that they decrease really quickly with the decrease of collision energy. For example, the cross-section is at the 54 is about factor 5, smaller than that at 200 GeV, so it's really challenging. So then let's talk about open heavy flavor. One slide on the method. So mainly open heavy flavor actually is very really challenging. Sometimes it's even more difficult than Quarkonium. So there are two methods to measure the open heavy flavor. One way is to do direct measurement, the reconstruct of the open heavy flavor hadron from the hadronic decay. So you have access to the full kinematic. However, the branching ratio is very small, and the signal to background ratio is very, very small. Another way is to through this semi-leptonic decay of the heavy quark, so we call it heavy flavor decay electrons. The branching ratio is larger, and another advantage is that the leptons can be easily triggered, so we can have a much larger integral luminosity for the study. So here I show you first the measurement at top energy, the D0 RA as function of PT in different centrality, the central collisions to peripheral collisions. So for D meson, we see in central collisions in all of the PT range from low to high PT, there is significant separation. This is indicates that there's a strong interaction between the chunk quark and the medium. And the red plot show you this lump of constituent quark scaled V2 as a function of the scaled kinetic energy. So they sort the circle for the D meson. You see, it is really consistent with that of the strange particle. So that's also indicates that probably the chunk quark reaches local thermal equilibrium at the top RHIC energy. And also last measurement from Phoenix, the heavy flavor electron suppression as function PT at the high PT, intermediate PT to high PT, there's strong separation, and it can be described by the model calculations and also close to the pi zero. And recently start also separate the heavy flavor electron from B decay and chunk decay. So here you see this is for the electron RAA from chunk decay, and this is from the B decay. You see there is some significant difference between chunk decay and the B decay electron. So this is consistent with the mass hierarchy of the photonic energy loss. Go to the flow, heavy flavor electron flow. This is for 200 GeV. The flow of the heavy flavor decay electron from 2-particle and 4-particle correlation. See, there's a significant flow in the intermediate PT range, and also can be described by the theoretical calculations for the heavy flavor decay electron. And recently start also separate the measure the V2 for the C2E, the electron from chunk quark, and that this is also significant flow and also consistent with the expectation of the D0 flow. and decay to electron. So and here also show you the V2 of the electron from bottom. So the solid square circle is measured from the event plane method, where the event plane is determined by the tracks in the middle rapidity. Is the similar rapidity as the electron, so they have some long flow contribution. So the shaded band is the estimation of the upper limit or lower limit of the long flow contribution. And the blue symbols is use the event plane determined by the fold particles. So there's large gap between the electron and the tracks used for the event plane reconstruction. So the long flow is highly suppressed. So from both the method, we see this non-zero flow for the B2E. So this is also indication that the bottom quark probably also interact with the median strongly. Move to the lower energy. So finish measure the RA of the heavy flavor decay electron in mid bias, showing in this blue circles, and compared to the pi zero in red circles. You see this strong separation for pi zero. However, since there's some enhancement yield of the heavy flavor decay electron. If you take the RCP, I mean the central to peripheral, you cancel out some uncertainty, and you see still there's some enhancement of the electron from heavy flavor decay in the intermediate PT range. And this phenomenon actually is different from that in 20 we go, but similar than that of deuterium gold at 20 GeV. So that could be some indication of a cloning effect. And however, if you look at the flow, although the uncertainty is large, you still see that all of the data points is above 0. So this is an indication for non-zero positive elliptical flow of the heavy flavor electron, although there is no suppression of the yield. STAR also measured the heavy flavor electron flow, the 200 GeV in red, 62 GeV in black, and 39 GeV in blue. So you see at the all of the data points actually is consistent with 0 because the error bar is pretty large. However, if you look at the PD below 1 GeV, all the data points actually is systematically lower than that of 200 GeV. And recently we measured this flow at 54 GeV with better precision. In showing in this solid circle, you see this data is pretty consistent with the flow in 200 GeV, showing in this star, gray star. So this is the amplitude is pretty consistent, and this shaded band is the estimation of the maximum of long flow. And the blue square is the flow in 27 GeV. This indication that at 27 the flow is smaller than that for 54 and 200 GeV. However, the uncertainty is large, so it's hard to draw firm conclusion. Compare the flow of heavy flavor electron to lead hadron in 54 GeV left plot and 27 GeV in right plot. So at 54 GeV, the heavy flavor electron flow is pretty consistent with the lead flavor. So it flows with lead flavor. There's still indication that at even 54 GeV, the heavy quark intact with the median strongly. However, at 27, so this is some hint that the flow is smaller than the lead flavor. But again, the uncertainty is large. Compared to theoretical calculations, so here shows the data in 20 GeV, 54 GeV, or 62 GeV, and 27 GeV, and the model from Texas A&M University, the solid bands, and also the PHSD calculation in the shaded band. It looks like the curve is below the data. However, if you take the uncertainty and also the log flow into account, then the calculation actually is consistent with the data at the intermediate PD above 1.4 GB over C. However, if you look at the data below 1 GB over C, the calculations below is smaller than the data. So conclude summary of the open heavy flavors at top energy. The yield is consistent with flavor dependent parton energy loss, and there's significant flow for Chang and also non-zero flow for Bolton. So there's indicates that the Chang strongly interact with the medium and reach local equilibrium. However, if we move to 62 and 54 GeV, we see Phoenix observed enhancement of the yields at 62 and start measure the significant V2 for heavy flavor electron at 54, and the amplitude magnitude is comparable to 20 GeV, and the flow also can describe by transport models. So that's the indication that the Chang is still strongly interactive with media at this energy. However, the cold nuclear matter effect may also play an important role in the yield. At the 27 GeV, there's still no yield measurement, and for photo flow, since that there's some different behavior between the electron and the lead flavor hadrons, but there's no enough precision to draw firm conclusion. Then let's move to the second part of my talk, the Quarkonium, my favorite topic. So I thought Enrico will talk about this. So it's really that people know know very well this RHIC puzzle. So RHIC start run things, measure the RA, and find that the suppression of the RHIC is pretty consistent with that from SPS at the mid-rapidity, and the suppression in the forward rapidity is stronger than that in the mid-rapidity. This is really opposite from the expectation from color screening, and these two puzzles, and that's actually is solved by introduce the additional contribution from regeneration. You see the two transport models can describe the data very well, the centrality dependence, and you see in central collisions, the contribution from regeneration is about 50%. And on this product, also lastly see that there is also expectation from the nuclear absorption also have very significant contribution in the central go-go collisions to suppress the yield by about 40%. So at RHIC, they really some interplay of the QGP melting and the regeneration and the cold nuclear matter effect. So if you move to LHC, Roberta, still the plot from Roberta's talk. So you see from RHIC to LHC, at the low PT, there's really strong enhancement. So this is a proof of the regeneration. And if you go to the high PT, where the regeneration is negligible, and also the cold nuclear matter effect is less important, you see the strong suppression of the happy gypsum, and the suppression is stronger at the HC than that at the RHIC, and this is also a strong evidence of the QGP melting. And I think this slide is realized from Roberta's talk. And then we move towards to SPS Energy, start measure the gypsum RA in 62 GeV in red, and 39 GeV in blue in mid-rapidity, and physics also has the same measurement at the forward rapidity. If we found that the suppression at the 62 and the 39 actually is consistent with that at the 20 GeV within uncertainties. And if you look at the energy dependence of this suppression, you see from SPS to RHIC, this pretty flat. And then from RHIC to HC, this is significant increase. This is really interesting, actually, from SPS to RHIC. I think there's a contribution from nuclear absorption and also QGP melting So there's competition because nuclear absorption has will result in increase of the RA as much energy, and the QGP melting should be decreased trend. So there's competition, and the start about 100 GeV, then the regeneration takes role, and also dominant at LEC. So this transport model calculations can describe this data pretty well. This is really very surprising because this really requires the careful treatment of all of the three effects. And at the 54 GeV, we see we also have a new measurement, very good precision, and we see there's no significant difference between this energy from 39 until to 200 GeV. If you put this data point on this plot, you see the precision is pretty good, and it fit into this the data trend, and also fit to this curve. This is by accident. I think this curve is really prediction. It's already exists there for more than 3 years. And look at the PD dependence. You see at this at 200 GeV, this PT dependence actually is pretty flat. And at 54, you see this significant decrease trend towards the low PT. And if you look at the first two data points, the data is systematically lower than that at the 200 GeV, although the significance is still is not so good because the uncertainty at the 200 GeV is large. And if you look at the dependence in different centrality, you see in all of the centrality there's an increased trend, and from peripheral to central there's more separation. So let's, I don't have much time, so I have to summarize the Quarkonium part. So at top energy, there's a significant separation at both low energy and low PT and high PT. Low PT, this contribution from both QGP melting and regeneration, and high PT, this is a clean probe of the QGP melting, and both then the transport models can describe all of the data, the RA, the V2 I didn't touch here. And if we move lower energy, 62, 54, and 39 GeV, we observed a significant separation. And the separation actually shows no significant energy dependence from SPS to RHIC. And there's increased PT trend at 54 GeV. So this data could provide further constraint of both the hot and the cold nuclear matter effects. If we move to lower energy, 27 and 20 GeV, actually currently there's no data yet. But you should be able to do that because although the cross section is about 2 times or 5 times smaller than that at 39 GeV, but we have 6 times more number of events. So we should be able to get some data with reasonable statistics and precision. So then this is one step closer to SPS. And if we want to do this physics, actually we can also do another scan. Is this system size scan. So STAR took a large data sample of isobaric, ruthenium, and zirconium data in 2018. This data was mainly for the chiral-magnetic effect. So they very large statistics, 3 billion mean-based events in each species. So in total is 6 billion, and the data is unblinded recently. We already observed very significant GPSI to plus and minus signal, and also deuterium D0 to K-pi decays. For the GSI, we observed about 50,000 low yield, and the significance is more than 100 sigma. I think this is give us a good lab to do this, study the GPSI suppression in fine centrality and PD beams. For example, I think this is close to Indian collisions, so the number participant in most central collisions is close to that of 20 to 30% go-go. And here I just show you an example, the cumulant high moments of the lead proton. So you see this blue samples is from the Isobaric data, and the triangles is from GO. And the light blue is the mean by SPP. You see this Isobaric data really have good statistics to fill the gap between PP and the central GO. So that's yeah, that this data could be expected to be shown in Quark Matter next year. So that's all. Thank you.
Thank you. Thank you, Zebo. Do we have questions remotely in the room? I may have at least two if nobody has one. I have a curiosity about the V2 measurements. So something like slide 13 or 14. So the range, the centrality range that is used is 0 to 60%, and the statistical uncertainty is still large. I mean, shouldn't we gain? Yeah, typically here, don't we gain a lot by like looking at 10 to 60? I mean, there is no V2 in the most central collision for sure, and that's where you have the highest background and maybe even yields. So couldn't we gain a lot by restricting a bit the centrality range? Do you know?
Yeah, here you see actually the dominant uncertainty is the systematic uncertainty. So that is mainly come from the subtraction of the photonic electron V2. Elena.
Hello, Zebo. Thank you very much for very interesting data. And I'm also curious about maybe slide 15, the next slide. Here's the data for 54 GV. No, 15. Can you go when you compare? Yes, exactly.
The one before.
Yes, when you compare your electron V2 with just hadron V2. And what I'm a little bit wonder that if you take your error bar seriously and look on blue points, they're systematically larger than, for example, pi V2 at low PT on the left plot. Do you think there is some physics behind, or it's a lack of statistics? And do you have a possibility to increase statistics in the future to clarify this point, or should we think about some physical effects?
Yeah, thank you for pointing out. Yeah, we also curious about this data points. I currently don't understand if there's any fix behind why at the low PT range the V2 is systematically higher than the light hadrons, also theoretical calculations. But increase the statistics is not possible, at least not the current run plans. So unfortunately, but we really call for the inputs from the theorists to explain this. Yeah.
Okay, thanks.
Do we have other questions? Yeah, Giuseppe.
Maybe just on this is PT of the electrons. Do you have more or less an idea how to go from PT of the electrons to PT of the parent hadron or charm? How would you expect to move with respect to PT of the hadron?
Maybe I can show you this plot. So actually, you see from the theoretical calculation, you see the magenta curve is from the calculation for heavy quark, and then the blue curve is for electrons. So this can tell us what is the difference between the quark and the electron. So I think the main difference is actually at the intermediate PTs, not at the very low PT. The decay will suppress the V2 at the very low PT.
Thank you very much.
Thank you.
Enrico.
Hello, Zebo. It's Enrico. I was looking at your slide 24, where you have these results for JPSI at 54 GV, which are let's say that they are already quite accurate. I was wondering if there is maybe it's impossible to have a full estimate of cold nuclear matter effects, but I was wondering if at least the shadowing contribution to these results could be evaluated, because this would be already interesting with such, let's say, a good accuracy.
Yeah, so actually we really call for the theoretical calculation for this. So we already contact the service, but not feedback yet. I mean, to extract the cold nuclear matter effect properly, we also need for the transport models to incorporate the cold nuclear matter effect, the hot nuclear matter effect to fit to this data, right? Or do you have any suggestion to how to extract the cold nuclear matter effect?
No, I hear. Okay, no, I understand. Let's say the breakup, it's a bit difficult to evaluate if there are no data, but at least one might seeing the X coverage at this particular energy, one could evaluate the shadowing effect, and this one could do maybe even without, let's say, need of theories. Let me say, it's still something.
Okay, understand. Understood. Thank you.
Okay, I may have a related comment. So in your conclusion on the Charmonia, you pretend that regeneration was evidenced at RHIC, while when I quitted Phoenix, we had some papers showing that the rapidity dependence of the RA could be just due to cold nuclear matter effects, and this kind of killed the hypothesis that there is for sure regeneration at RHIC. There may be, but you really don't have the evidence, because it can be a mix of, as you say, actually, I mean, it's probably a mix of cold nuclear matter effects and maybe of regeneration. Did I miss something, or were there like super precise new measurements that really show regeneration? And that's related to Enrico's comments, because when you look at the centrality dependence, then maybe if it grows with centrality, then maybe you start being convinced that there is regeneration. We don't hear you anymore. Try again.
Hello?
Perfect.
Okay. So actually, I think this is no direct evidence from the data, but so actually the transport model compare the many data as function of rapidity, as function for PT, and I think they have a fair description of the data. So I think I cannot imagine if without the regeneration, how these models can describe all of the data.
Okay, so it's not because one model does it that it's an evidence, but I will look at the details.
No, two models, two models.
You have an evidence if no models can do it without what you're claiming, I think. Do we have other questions? If not, then thanks, Zebo, again.